My name is Lucas Fryzek. I'm a new hire at Igalia. I started at the beginning of this year. I'm not new to graphics development, but I am new to the open source community and contributing. And so when I started, my colleagues had recommended that getting Freedreno to run on Android would probably be an interesting project to start with, to get familiar with Mesa and to start contributing stuff upstream. So in this talk, I'm going to cover a few things, all of them related to Freedreno, all of them related to Android. I'm going to talk a little bit about the state of the drivers with the Adreno GPUs, and why this is important when you're trying to run something on Android. A little bit about why you might want to do this, how you actually build Mesa to run on Android, driver changes that are necessary to run on Android, and then some areas of needed improvement for Android support in Mesa. But to start off, in anything like this, it's important to show your work. So when I started my development, a lot of it looked like this, where you have broken rendering. That line in the middle of the screen is not my problem. That's a broken device, so I do apologize for that. It's not a problem I caused. But all the broken rendering behind that is a problem that I did cause with synchronization, things not working, the stuff being displayed before the GPU has actually finished rendering it. But in the end, it looked like this, where stuff actually looks like what you want it to look like. The capabilities actually report the driver as being Freedreno, and many applications running without any fault at all. So to start with the state of drivers for Adreno and Qualcomm GPUs, there is a tale of two drivers here. There are two kernel mode drivers that give you access to Adreno GPUs. One of them is a little bit nicer. It's the MSM driver. It's your friendly neighborhood upstream driver that is a lot easier to target, plays really nicely with Mesa. And then there is the less friendly KGSL driver, which is the driver that Qualcomm supports on Android, and it's what their proprietary user space supports. And so the work that I ended up doing was trying to get Freedreno actually to work with KGSL, because that's what you end up using when you run Android on a Qualcomm device. Now, there are some other things that are nice about using KGSL. One of them is that support for every SoC for Qualcomm is not upstreamed. So if you do have a use case where you're using Android, it can be a lot of work to try to merge upstream code into a downstream branch. And another interesting benefit I learned about as I was working on the project was that it provides the ability to run both Qualcomm's proprietary driver and Freedreno on the same hardware, in like a CH root, or just switching which driver is being loaded at runtime. And this was a pretty interesting thing, and I got a lot of, attention on my work, because apparently Panfrost already supports this, and people like to run CH roots on their Android devices to use hardware installation in a Linux desktop environment on Android. So, some notes about the work I did. It wasn't entirely from scratch. Turnip already has very good support for the KGSL kernel mode driver. So a lot of the work that I did was actually based on the Turnip developers. So any Turnip developers watching this talk, thank you very much. You made my life a lot easier. And another nice thing about Freedreno is that the interface to access the kernel mode driver has already been pretty heavily abstracted. There is a interface in the source Freedreno DRM folder that provides a convenient API to accessing a kernel mode driver. In what is upstreamed right now, it currently splits support for MSM and the virtual I/O driver. And it's what I use to get all my work started for a different kernel driver backend. Now, all the work I did was on a Pixel 4a device. This was convenient because it has an Adreno 618 GPU, which is already supported by Freedreno. So I didn't have to worry about, driver bugs at the same time I was trying to get this device working. I was using both two versions of the Android NDK, version 25 and 13. And later in the presentation, I'll talk a little bit about why there's two different NDK versions that ended up being used. And the other convenient thing about using a Pixel device is Google has this handy tool for Android where they have a bunch of ROMs available and a tool to flash them to your device. And this is very important because when you're messing with the system partition on an Android device, you need a user debug ROM that actually lets you unlock the file system because Android can be very locked down. So in my case, since I'm using a Pixel device, I can just go use this nice tool from Google, go find a user debug ROM for ASOP, download it on my device, and not worry about building a ROM myself. If you're trying to support this on a non-Google device, I think there would be a lot more work trying to get the user debug ROM set up, which would include building Android yourself. Now, that's getting started. What about building Mesa on Android? Well, it's actually a lot easier than you think. It's probably the easiest part of this project altogether. If you're targeting the Android NDK, it gives you a normal tool chain that you can just target with Mesa on cross files. And in fact, the Turnip developers have nicely written an Android guide for building Turnip on Android that you can conveniently use to build the same work that I did for building Freedreno. And like cross-compiling to any other target, there's some Mesa configurations that you have to set for what platform you want. There's Android-specific ones for what SDK version you're targeting. So in my case, all the work I did was targeting SDK version 15 or 25, sorry. So I had to put that in there. There's Android stubs that you have to build just to deal with libraries that you don't necessarily have access to at build time. And of course, what drivers you want to target. In my case, Freedreno, and Freedreno also has this additional argument for kernel backends you want to build. So you, for the work here, want to target the KGSL kernel mode driver. Now that's great. We built something, but this isn't friendly Linux land. How do you actually deploy what you did on the device? You can't just set up an install folder, LD preload your install folder, and set whatever environment variables Mesa wants for loading the right driver. It's not that simple. You have to do a little bit more work and figure out what the heck Android is doing under the scenes. The Turnip developers have kindly wrote in that tutorial how to actually do things for Vulkan, and for doing things for OpenGL is very similar on Android. And for Vulkan, there's files in the vendor lib64, so a system partition for where the driver files are. In order to access those files so that you can write to them, you need to unlock the system partition, which is not that hard. As long as you have the user debug ROM, you can just run some ADB commands, and then you have read-write access to the system partition. And to actually find out what libraries Android is loading, thankfully Android is in fact open source, and we can see what's going on there. And you can just go into the EGL loader source code within Android and actually look at what libraries it loads, and finds out that it loads libraries from the vendor lib64 EGL folder, and it loads these libraries based on a vendor name. So you have to add a vendor name to what Mesa builds so that it can actually load the driver that you're trying to work with. So in my case, it's the Adreno one, so I had to add the EGL Adreno and the GLES1 Adreno, and those are both used for the EGL implementation and OpenGL ES1 implementation respectively. The GLES v2 does not have the vendor name appended to it, and it provides the implementation for GLES2 and beyond. Now, if you go and you replace those libraries, and you go and you try to run something, you'll quickly find that it's still using the old driver. You run the GL info app on Android, you'll see that Qualcomm's driver is still loaded, and you start scratching your head and going like, okay, what's going on here? And then this is another case where I'm happy that Android is open source and there is some documentation on this thing. And you'll find out that Android preloads the OpenGL driver that it uses at initialization, which is, I guess, good for performance on the system, for doing things like the system UI rendering and for applications, but it's not nice when you are trying to iterate on development and you don't want to have to restart your device every single time you make a driver change. So thankfully, there's a way to disable this preloading feature, and it's actually documented publicly within Android's documentation. There's this disable GL preload property in Android that you can override and set to true, so that anytime an application starts up on Android that's going to use OpenGL, it will reload the driver or the library. Now, the other thing about this setup with the kernel mode drivers is that Freedreno also expects some environment variables to be set, and on Android, you don't really have environment variables. They have their own system called properties, and thankfully, Mesa developers have already thought this through and have added an abstraction to the environment variable system so that if you're running on Android, it will conveniently use props like environment variables with the added note that any underscore in a property name gets replaced with a period, and if the prop doesn't have Mesa in front of it, it will add Mesa in front of it so that they're all in the Mesa namespace. But doing that, we can now set all the environment variables we need to allow the device to, or the driver to load properly and start running. Now let's talk about testing. So with everything that I just talked about right now, if you want to go and open an Android app like an APK, it will go and it will load the driver and use it. You can open things like the GL Info app, and it's going to report all the capabilities that Freedreno reports. It's going to report the name that Freedreno reports, and that's great and all, but those aren't usually what graphics driver developers use for testing most of the time. A big part of our life is CTS, and thankfully CTS can be built as a APK so that you can run it on Android and actually see that your OpenGL implementation is conformant. But in my case, what I was doing is comparing my CTS results on Android against CTS results on Linux to make sure I haven't broken anything in the process. But this is not the most convenient developer environment. CTS is not quick when you're running through the entire test suite. I know probably a lot of you like to run things in parallel with DEQP runner. So I think you can imagine anytime you want to run CTS, having to sit through the whole thing is not desirable. So something that I did learn is that you can actually run command line applications on Android. The developers who worked on Freedreno reverse engineering very early on in the process set up this nice reverse engineering tools repo where they set up some application infrastructure that allows you to build OpenGL applications that you can launch from an ADB shell. And if you're not familiar with an ADB shell, that's basically just like Bash on your Android phone. You connect it to your computer, you type in ADB shell, and then it gives you a shell that you can start running commands on your Android device. So this is great. You can start building OpenGL applications. They have a nice framework put together, so you can look at that and figure out, okay, if I want to run an OpenGL application, I can do this. The big caveat on all of this is it's using EGL p-buffers, and if you're not familiar with p-buffers, they're off-screen surfaces. So you can run stuff, but it's not going to be shown on the screen. But in the case of testing, we're not usually looking at the results. It's a lot of just comparing results. So this is really nice when you're trying to rapidly iterate for development. Some caveats about this repo. So it has build scripts already set up, but everything in it targets NDK version 13. And there's a specific reason it targets NDK version 13, and that's because after that version, Google stopped shipping a lot of stuff in the NDK. And one very useful thing for us is that Google used to ship debugging tools with NDK 13. including GDB server, which is very useful when you're running applications in this environment, because if you have some kind of bug, it's nice to actually debug it, and you do that with the normal Android debugger within Android Studio. So in this case, you can launch your application, you can move the GDB server application from the NDK to the device, and then use it to launch your applications that you built as more normal Linux applications, and then run them from the ADB shell. And then you can connect it to it from your computer, get a source code view, set breakpoints, do everything that you love to do with GDB. But we can even take it further. Although the stock CTS, when you try to build on an Android platform, only lets you target like an APK build, we can modify the CTS Android platform to build more like the Linux one, where it's a command line app, and then you can, again, copy that to your device, and then you can run it from this nice ADB shell environment. And in fact, if you keep repeating what I'm doing here, there's a Cargo NDK, which is a implementation of Cargo targeting Android devices. That lets you build basically anything in the Cargo repos for Android, which includes DEQP runner, which is great because now I can run tests and they will finish before the end of the day. So the source code changes to get this all working were only 900 lines of code. It was not that complicated. The majority of the changes were in the KGSL backend folder that I created in source Freedreno DRM. But there were also significant changes in this nice file called Platform Android in the EGL implementation. I'll start just with my changes on the KGSL backend. This was responsible for doing things like buffer object allocation and mapping, querying properties from the kernel mode driver, submitting command queues to the hardware, and handling synchronization. The majority of this code came from Turnip. Like I mentioned very early, Turnip already has support for this, so a lot of it I didn't have to worry about too much. I just had to translate it to the Freedreno backend interface. So it was a lot of copy pasting, and throughout the process, there was some code that could be moved to be common between Turnip and Freedreno. But not all of that has been done in the work I've been doing. So there's, again, always stuff you can do to clean up the code base and make it look nicer and work nicer and reduce copy paste. Some interesting quirks about the KGSL backend that caused me a few issues. There's no reference counting on buffer objects that are created within the KGSL kernel mode driver. So if you try to free a buffer that's currently being used by the GPU in a normal DRM driver, it will get freed at a later point once there's no references to it anymore. KGSL, as soon as you free it, it's done. And the first implementation where I got things running, I ran into interesting problems where I would MMU fault quite frequently because memory would be freed right in the middle of the GPU drawing it, and it was not fun, but it was fairly easy to figure out what was going on there. Another thing that caused issues was the KGSL kernel mode driver in the interface to pass commands to it. It has a offset parameter that is completely ignored, and the GPU address is the only thing that's inspected, so you have to make sure that you include the offset in the address that you actually pass when you're telling KGSL the command object that you want it to run. There were some necessary backend changes that the Freedreno interface that I mentioned before didn't actually accommodate that were necessary in order to make it more general to different kernel mode drivers. The big thing was the way that frame buffers are allocated in Android are very different, and they need to be mapped in a different way. I'll talk about it a bit later, but they come from a different memory allocator, which is a lot of fun to deal with, called Gralloc, and they need to be mapped differently than buffer objects that you allocate from the KGSL directly. So in the Freedreno backend, I needed to add support for a per backend implementation of mapping and importing DMA buffs to handle this unique KGSL behavior. Now those were nice changes. They were easy to make for the most part. The platform Android changes were not as nice in EGL. This was a bit of a mess to deal with, and I'm going to talk a little bit about some of the not nice stuff about working on this project and some of the big problem areas that still exist within there today. So on Android, you have this nice graphics allocator called Gralloc, which is used to allocate what it sounds like graphics memory. In our case, all the frame buffers for Android apps and for system UI and stuff like that are allocated in Gralloc and then passed to us, the driver, and then we do our rendering to them. An interesting thing about Gralloc is that it's implementation specific, but another thing about it is because Turnip runs on Android, they already have code to interface with it, so I wasn't starting from scratch again. But you go and you look at Turnip's code, and it looks like this. I don't know how obvious it is here, but if you look right there on the second line, that's not what I would call an API. You're just looking at an array of ints, and it's not documented what they're doing. There's some magic numbers there about handle data, like what exactly does that mean? And then you quickly find out that there's no externally accessible API to access internal data on per device implementations of Gralloc. So it's not really meant to be general. And that code that I just showed from Turnip, the way that they figured that out is they looked at the Gralloc source code for Qualcomm, they figured out where the data is in the structures and just hacked it and made it work. And it works. You can draw the surfaces. It's not pretty, but it works, and it may or may not break in a future update. Just trying to get things working, I implemented the same interface for platform Android, but this quickly becomes quite unmaintainable. I would think if the more non-DRM compliant kernel mode drivers got support added in Mesa, because like I mentioned, there's no kind of general API to access this in this current implementation. The code that exists right now in platform Android can handle DRM drivers that are running on Android. So some devices already work well if you build an upstream kernel with and you use a recent version of Mesa. But in my case, where I'm trying to use the KGSL kernel mode driver, that option doesn't exist to me. I have to use the Qualcomm specific version of Gralloc. There is, in fact, a newer API that is supported in Android, and it's under this file called platformandroidmapper.cpp, and there is a externally accessible API to interface with the allocator that I think would allow us to do everything that we want to do. But a big issue with it is that, as far as I understand, it cannot be used with the Android NDK, which is the main setup right now for building Mesa to run on Android, both in, from what I know, Turnip and my work in Freedreno. The big issue between them is this is provided by the Android system, and something Android does to kind of differentiate things because of, and I'm not an Android expert, so I don't know the specifics here, but anything that's built in the system that uses C++ and it's like using the standard library, it puts it in its own special namespace. And then when you try to build NDK apps, so stuff that's running as like user applications on Android, they put all the standard library in its own namespace. So if you try to access any of these functions, you'll find out that you can't actually access them due to namespace problems. The other issue that I found out is that you can actually use these functions if you build Mesa in tree with Android, like building, for example, ASOP. But it's my understanding that this setup of building Mesa in tree with like ASOP is likely to be deprecated. This is currently the alternative way to build Mesa without the NDK and get access to that namespace. So like I said before, I'm not an Android expert, so I'm not sure how useful this is, but if we had access to this from a convenient way to build, I think that would solve a lot of the problems with having a per driver implementation of the Graalvk backend. So I'm going to talk a little bit about bugs I encountered. So a big caveat to all this work, none of it is upstreamed. I ran into some problems that weren't really related to the Android support, but were more Freedreno bugs that prevented it from working on Android in its entirety. The main one was an issue with surfaces allocated by Graalvk, and the fact that they don't necessarily respect GPU limitations. And so in my case on the ACE, the GPU in the Pixel 4a, the blitting engine, when it reads pixel data to copy it, it does it in 16 by 4 chunks. And if the frame buffer that you're trying to write to or read from if it's not aligned to 16 on the width or 4 on the height, you will read outside the bounds of that memory, and you will trigger a fault, which is what ended up happening for me. Whenever something was rendering towards the bottom of the display, it would trigger an IOMMU fault, and a lot of the times that would stop the GPU from working or stall or cause flickering. So in my opinion, this is kind of the biggest issue from actually making my work worth upstreaming. As it stands right now, if you try to use it, the Android UI will frequently cause this problem I'm talking about and start flickering. Most applications you run will work fine. Just by an incredible fluke where on the Pixel 4a device, the screen resolution is divisible by 16 on the width and divisible by 4 on the height. So if you have a full screen application, it's great. You're not going to run into this problem. Unfortunately, the Android UI is not running full screen, so it does run into this problem. So this led me to a different path where I started looking into reverse engineering a little bit, because the Qualcomm blob driver gets the same surfaces that we do and is somehow able to render to them without causing this issue. So they're doing something a little bit different on the copying. But again, this is where things got kind of stuck. So I'm just going to talk a little bit about the Freedreno reverse engineering tools, because the last thing I did in this work was getting them to work for debugging this use case. And if you're not familiar with them, Freedreno has a diverse set of tools for inspecting the GPU state, but they're pretty much all designed to run from the command line in a Linux environment. So if you're trying to debug an Android APK, they're not that helpful. So in my case, one of the key tools I wanted to use was one called librap, which is a library that allows you to trace the commands being submitted to the GPU. As it works with both the Freedreno and Qualcomm driver, so you can capture traces between what Freedreno is doing, what the proprietary driver is doing, and start comparing them and seeing where the differences are. Unfortunately, it uses the LD preload mechanism to override system functions for things like open, read, write, to ioctl, for example, to actually capture those functions and then write them out to a file that you can use for comparison later. And because of the way Android works, you can't just LD preload, launch your APK. It's not as nice in Linux as Linux in that regard. So how do you actually make this work with APKs? Well, the first thing is trying to figure out how you can override system functions. And there is actually a way on Android to set environment variables for applications that are like Android applications that are being launched. And there's this wrap property that you can use. And the Android launcher will use that to set environment variables when it itself launches processes. So you can go ahead and use the ADB shell to set this wrap dot and then app name for whatever the app that you're testing is property, and then override environment variables like LD preload to get it to preload the librap, and then use that to start dumping the GPU command stream. Now, one big issue I ran into with doing this on Android was I quickly found out that multiple threads would suddenly start accessing the KGSL file descriptor. and the libwrap library was not designed to handle this. And so you'd go and you capture a trace, and it would not make any sense because you'd have commands inserted in the middle with other ones that were not coherent at all. And so I had to do some work in making the libwrap library thread safe, and so that this problem wouldn't happen. You could actually read the traces and they would be coherent. And that work is in fact already upstream to the Freedreno reverse engineering tools repo. So a couple conclusions about this. If anyone is looking to get their driver in Mesa running on Android, a lot of the infrastructure is already there. Like I said, there's only 900 lines of code roughly required to get this working. If it's a proper DRM driver and you're able to run that on use that on an Android system, then there's a good chance it will likely already work. If you want to use a downstream kernel mode driver and Graalvk implementation, that's where things get a little bit more messy. But a lot of this is open source, so even though it's messy, you can go see what that library is doing to get the per device specific information that you need for memory allocations to handle the stuff that you need to handle. Development is a lot faster when you do work from ADB shell. When I started, I was trying to figure out how I can do this in a more efficient way, trying to set up scripts that would launch APKs and get the Android Studio debugger connected to things so I can inspect the state. And it just, maybe if you've been doing Android development for years, this would be easier and you'd be more used to it, but I have not. I'm used to the Linux command line, and I prefer an environment that looks like that. And so once you can set up an environment like that on Android, I found development to be a lot easier and make things much quicker for doing my work. The last big conclusion is one of the biggest problems I think in Mesa right now for Android support is the Windows system integration. Like I mentioned, it's pretty ugly for how it's handled right now for both Turnip and Freedreno. Hopefully there are Android experts around that can comment a little bit more in case I'm missing something obvious about how we can get device-specific information in a way that doesn't require ugly hacks. So, this is something I would like to see improved in my changes, but at the moment they work without that, but you just have to be okay with a little ugliness. That's everything I have for my presentation. If you have any questions, feel free to ask, and the obligatory We're Hiring page, if you're interested, you can apply at the link. Sorry, I can't hear you that well. Could you get the microphone?
It is not strictly a question, but just thanks for trying Freedreno on top of KGSL. So this is not a thing that we usually do, and thanks a lot for your experience. Okay, small question. So at some point, a few years ago, we had to also modify the, okay, it doesn't fully work. We had to modify Skia to treat Freedreno in the same way as treats the KGSL. Did you have to modify Skia in this in any way or not?
No, but Skia would complain a lot because Freedreno doesn't support I think it's YCRCB textures. But so as far as I understand, and again, this was a lot of my first experience dealing with more Android system level stuff. A lot of the UI in Android is rendered using Skia, and when I had it running under Freedreno, it just worked. Everything rendered correctly with the exception of when that IOMMU fault would happen, and then it would cause stuttering and flashes in the display. But when those issues weren't happening, the Android UI looked identical to running on Qualcomm's proprietary driver. And as far as I understand, all of that's running on top of Skia.
I heard the rumor that Google is pushing for basically at least the kernel side open drivers. Do you know anything about that?
No, I don't. I'm sorry.
Just a curiosity question. Do you feel like Google is closing the development area of the Pixel ecosystem?
The closing how? Sorry.
For example, I used to use Termux, and several commands that I already don't remember do not function because they are not available at user level, only if the phone is rooted.
Okay. I'm not sure I fully understand the question. Like in this case, the development that I did, you could only do when the phone is rooted because you need access to the system partition to replace the libraries. But if you're, you know, a device, if you're shipping devices, you have control of the image that goes on that device, and then you would just include the Freedreno driver in the system partition at that point, and you wouldn't have to like root it. I mean, obviously the end user at that point can't change the driver, like it can only be changed by system updates. But you know, the Android operating system is pretty restrictive in what a user can do on the device. So a lot of, you know, hacking like this, you have to root the device to just get access to what you need.
Pixel devices are pretty good for getting a user debug image, and those you can always get root on. Other devices, you're at the whim of the vendor. It's not up to Google.
Yeah, so like at the beginning here, I'll just go back a couple slides. So Google has this flash.android.com tool. As far as I know, it's supported on all the Pixel devices. You can find like user debug ROMs for a bunch of different configurations. In my case, I just used ASOP, and this gives you root access. Like it's very straightforward, like not complicated at all to root the device and actually have access to start doing development like this on an Android device.
So before all, thanks for your talk. I think it was really interesting, and I wanted to ask, how do you feel about the fact that maybe users are being locked down for using like free and open source replacements? Like, for example, let's say Freedreno, it's included in a build for some custom ROM. After all, safety net is rowing towards the opposite direction, and after all, end users, like for example, let's say Google Pay or some Google services that are not easily replaceable by open source alternatives because trust and cybersecurity and all that kind of stuff. How do you feel like we can row towards completely Google-less or not Google-less, but let's say like free and open source, entire functionality, no restricted end user experience?
Okay, so it's an interesting question. I have to say that personally, I don't like the fact that if you run like a Google app list, like Google services list device, a lot of applications you can't use. I find that fairly annoying, especially because there are things that are usually stuff that they're not like silly games. Like it's your banking app that doesn't work, or it's like your insurance app that doesn't work. So, no, it's not very nice. My opinion on the matter is I think it kind of goes against the spirit of keeping things open to the user. Like me personally, my experience growing up as a developer was, you know, Linux is very open. You could, if you want to see how something works, you can go look at the source code. If you want to start hacking on something, you can go do that. You can build it, and I feel that it restricts that availability. I do like on the Pixel devices specifically that it's easy to set up a development environment where you can start accessing system stuff, and I think it gives you some of that freedom again. But yeah, I think I'm not a security expert, so I can't comment on if it's really that much more dangerous for a user if they have a rooted device to access their bank information. But from the experience of someone who used things like hacking on the system as a way to learn how to program, I think it's not great. Any other questions? All right. Thank you.